Let u be some scalar function of Rn. So it's defined on Rn, at least in some subset of Rn, which we call, as usual, omega. On the boundary of omega is, as usually, denoted del omega. We recall that the gradient of this scalar function u is a vector function which has the following components. In the first component, we have the partial derivative of u with respect to the first variable, x1. The second component is the partial derivative of u with respect to the second component, and so on. The divergence is in some sense the opposite. It means that if we have instead of having a scalar function, we have a vector valued function with components w1, w2, and so on. Then the divergence of this vector function is defined as the scalar function, which is the sum of all these items. The first term is the partial derivative of the first component of w with respect to the first variable. The second term is a partial derivative of the second component of w with respect to the second variable, and so on. We call this the classical Poisson equation, and it's called a strong formulation of the Poisson equation in the case where f is some scalar function defined on this the subset omega. So this may be some heat conduction equation with some source, internal source, heat source, which is the function f of x. The divergence of lambda x, where lambda x is called the thermal conductivity, multiplied with the gradient of u equal to minus fx, is some more general version of this Poisson equation. So this is called a strong formulation. Omega may be some square, generally some smooth, or it does not need to be a smooth boundary. It is enough for most purposes that this surface is Lipschitz continuous, as we have been speaking about earlier. If we just let us show that this is some generalization of this function, this equation, because lambda gradient of u is just gradient of u where we have multiplied the conductivity in each of this component, and taking the divergence of this gives this expression. And if lambda now is a constant, then we can take this constant in front here, and then we just obtain this equation with some constant lambda outside. And this constant, we can divide it on both sides, the equation, and then we get something which is very close to this Poisson equation. Note that the normal derivative of u, we have just let us illustrate it, see the illustration of it. This is a normal vector, unit normal vector. It has length equal to 1, and it points in the normal direction of the boundary at every point here. So this is interesting and important quantity, and it turns out to be equal to the gradient of u, which is a vector function multiplied with the normal vector. So in the case when this normal derivative is known on the boundary, we call the problem of the Poisson problem for a Neumann problem. it's called a Dirichlet problem if U is known on the boundary. This has been discussed also in the first week. Let us just mention this formula, which is, we are not going to prove it. It's possible to prove it by using Gauss theorem, which is an important result in vector analysis. It takes the following form. If we have some function which we call phi, and we have a vector function which we call w, and we take this, by the way, this function phi is defined to be assumed to be a scalar function, then the integral of the product of this function with the divergence of w turns out to be equal to minus the gradient of theta multiplied scalar. This is a scalar product with w. This integral is taken over omega plus this boundary integral, where we are integrating along the boundary of theta omega multiplied with n. ds, we use the symbol ds in order to not confuse it with this integration. So we are integrated along this boundary on this this term. This term consists of the boundary integral. So if we now do the following, we take the Poisson equation, or the generalized Poisson equation, which is of this form. We call it the star equation, and we on both sides multiplied with the function phi. Then we can we of course get a new identity and integrating this equation on both sides over the space omega, we obtain, by using Green's formula, the following. So we are first multiplying with this function phi on both sides and integrating and using the Green's formula here. Here we just recall, instead of using w here in the Green's formula, we use now lambda grad u. So now we have replaced w by this in all terms. So here we have replaced it, and here we have replaced it. Then we obtain this. This Green formula turns into this equation.